Hello and welcome. Now that we've proved the Cantor-Bernstein theorem, we can now show that inequalities among cardinalities satisfy some natural conditions. These arise in other contexts as well, and so we have a more general name for them, namely the partial order on a set. And this is defined as the following. Is a relation x is less than or equal to y amongst elements x and y of S, such that if x is less than or equal to x for any x in S, and if x is less than or equal to y and y is less than or equal to x, then it must be the case that x equals y for any x and y in S. Finally, we have transitivity. If x is less than or equal to y, and y is less than or equal to z, then it must be the case that x is less than or equal to z for any x, y, z in S. For example, with our case of cardinalities and sets, the set of all subsets of a set S is clearly a partial ordered set if A is less than or equal to B means that A is a subset of B for any subsets A and B in S. And we have that the set of natural numbers has a partial order defined on it, namely that if A is less than or equal to B in the standard way, or by considering cardinalities. As in the case of equivalence relations, the notion of a partial ordering can be applied to relations among sets as well as to relation among elements of a particular set. So in particular, it can be applied to the relation the cardinality of A is less than or equal to the cardinality of B. The relation 1.15 is a partial order on the cardinality sets. You may find it useful to go back and review the video in which relation 1.15 occurs. The reflexivity of the relation 1.15 is clear since the identity mapping iota from A to A that associates to any set A and A the same element iota of A is equal to A as an element of A is clearly injective and is transitive, since if F from A to B and G from B to C are injective mappings, then the composition G of F from A to C is also injective. Antisymmetry, on the other hand, is far from clear, but if we consider the Cantor-Bernstein theorem again, we can get there, and this is sufficient for the proof to show that it is a partial order. Now we continue with Cantor's theorem, which says that the power set P of A of any set A has strictly greater cardinality than A. That is, the cardinality of the power set of A is greater than the cardinality of A for any set A. To prove this, we go through the following shorter proof than before. The mapping that sends each element A to the subset A is a subset. The element A is a subset of A is an injective mapping G from A to the power set of A. We note that A includes elements, while the power set of A includes subsets. So we have an element being mapped to a subset. Hence, we have that the cardinality of A is less than or equal to the cardinality of the power set of A, since we have an injective mapping. Now, to prove that there is not equality here, it is a strict inequality, we will go through a proof by contradiction, namely, supposing that there is a bijective mapping between a set A and its power set. This means that the subset E, which is a set of all x in A, such that x is not an element of f of x, is a well-defined set. Also, is possibly the empty set. So since the mapping F is assumed to be surjective, then the subset E must be the image E is equal to f of A for some A in A. However, if A is an element of E, then from the definition of E, it follows that A is not an element of f of A is equal to E. While if A is not an element of E is equal to f of A, then from the definition of E, it follows that A is an element of E. This is a contradiction, though, because either case is a contradiction. Therefore, there cannot be a bijective mapping F from A to the power set of A, and therefore the proof is finished. In particular, of interest is the fact that the cardinality of n is less than the cardinality of the power set of n. So the set of all subsets of n of natural numbers is not a countable set, but is a strictly larger set, namely a set with a larger cardinality. The set of all subsets of that particular set is properly larger still, and therefore we have no end to the size of possible sets and impossible infinities. Nonetheless, there are many sets that appear to be considerably larger than n, but nonetheless are still countable. And we can prove this using Cantor's diagonalization theorem, which is as follows. If to each natural number n there's an associated countable set E sub n, then the union E, which is a union over all natural numbers n of E of n, is also a countable set. Note that it is very important that the sets En are countable. And this is how we prove it. And this is where this famous theorem comes from. Since each set E sub n is countable, then the elements of E sub n can be arranged as the first, the second, the third, and so on, since it's countable. So if we want to consider the union big E of all of these E sub n's, then we can write them out like this. For instance, we read this, that this is the first element of the first subset, is the second element of the first subset, and so on, and it's the first element of the second subset, the second element of the second subset, and so on in both directions. Now, to prove that this union is countable, we simply need to find a way to count through every element in this array such that none are missed, and we do not go on, that we only go on infinitely many times. We can now rearrange this array by starting with x11 and proceeding along increasing diagonal with x21 followed by x12, then along the next diagonal from bottom left to top right, and so on. If a row n is finite, though, simply the xn sub i's, so if every point sufficiently far along x of the nth row, there will be blank spaces, but this is not a problem as we can simply skip them in the ordering. Then we can write out all the elements of E in order, namely in this order. Therefore, we associate this the first, the second, the third, the fourth, and we have an obvious injection and bijection between E and the natural numbers. Therefore, we know that E is countable. For more detail on drawing those diagonals, consider following the mouse here. This, then this, then this, then this, then this, then this. Increasing diagonals from the bottom left to the top right. We now consider the set of all finite subsets of n and show that it is countable. We can do this by induction. First of all, it follows by induction on n that for any natural number n, the set E sub n of all subsets A of n for which the cardinality of A is n is countable. It's clearly the case for n equals 1, and if En is countable, then we can simply append one element to each of these sets A to create a new set in E sub n plus 1, and we see this is a subset of the union over all natural numbers of I unioned with that set A. Therefore, we see that En plus 1 is countable by Cantor's diagonalization theorem, since this is a countable union of countable sets. Therefore, since all the sets E sub n are countable, it again follows from Cantor's diagonalization theorem that the set E is the subset, E being the union of all of these subsets, each of which are of length n, is countable. This suffices for a proof. Thank you. And with that, we end this section 1.1 on sets and numbers, and we'll proceed with section 1.2, covering more algebraic structures such as groups, rings, and fields. Thank you.